Good day and welcome back to part 3 of our discussion of the chain rule. And as mentioned at the end of the previous video, we are at that point where it's so important to go through and practice examples because as we move on to more advanced topics and applications, differentiation is going to become a smaller part of a larger problem, so we really do want to be quick and efficient with our differentiation skills. So, reminder to get started, we've been talking about the chain rule, which is used to differentiate a composition of functions. And the derivative of f of g of x is equal to the derivative of the outside function evaluated at the inside function multiplied by the derivative of that inside function. And it's also worth noting that kind of a common occurrence is when we differentiate 1 over a function. This could be something like cosecant or secant, or it simply could just be 1 over x plus 2. In order to differentiate that, we could use the quotient rule, but it's also worth noting that we can algebraically rewrite as f of x to the minus 1 power. And when we do so, it can be differentiated quite conveniently using the chain rule. We differentiate the outside function, the minus comes down front, and the new power is 1 less. We evaluate at the inside function and multiply by the derivative of the inside function. So minus f prime x all over that function f squared. And to be as clear as possible here, let me note there's nothing to memorize. It's really just introducing this technique, so it's something we have to use if we encounter this scenario. So on to our first example. Let's find the equation of the tangent line to the curve given by the function sine of sine x over cosine x at x equals pi. So recall, as usual, if we want to find the equation of this tangent line at pi, it's going to be f prime pi x minus pi plus f of pi. So we always immediately jump to that starting point and note we needed to come up with 2 values, f of pi, f prime of pi, where f of x is the function given by sine of x, all divided by cosine. So immediately we can do this first function evaluation. So f of pi would be sine of pi, all divided by cosine pi. And remember, when it comes to evaluating trig functions at common angles, we always need to do so. So cosine pi, you would tell me, is what value? I agree, minus 1. And sine of pi is 0. Furthermore, sine of 0 is also 0. So f of pi is the number 0. The other value that we need in order to have the equation of our tangent line involves a derivative. So we will go ahead and differentiate using the quotient rule. The quotient rule tells us low d high. Now I'm going to go ahead and just differentiate this function directly. So the derivative of the outside function sine is cosine. We evaluate that at the inside function sine, and we multiply by the derivative of the inside function cosine. And to make sure there's no confusion, note that this cosine of sine x times cosine x, that came from differentiating the numerator. So the quotient rule, once again, we have low d high minus high d low, and the derivative of cosine is minus sine, and this is all divided by cosine squared in the bottom. And let's go ahead and just simplify slightly, and then we'll substitute in 0. So the first term in the top would be cosine squared times cosine of sine of x, where we have grouped together the two cosine terms to be cosine squared. Minus a minus will make that a plus sine of x times sine x, all divided by cosine squared. And now we can easily substitute in pi. The hardest part might be just writing everything down. So we have cosine squared of pi times cosine sine of pi plus sine of pi times sine of pi, all over cosine squared of pi. So just a few quick trig values to remember. Sine of pi is 0. 0 times anything is 0. That second term vanishes. Cosine of pi is minus 1. Cosine squared of pi would be minus 1 squared. So what we are left with now very efficiently is a 1 from the cosine squared of pi times cosine of 0, which is 1, plus the 0 term which vanishes, all divided by 1. So after all of that work, we find that f prime of pi is the number 1. And the equation of our tangent line, if we now kind of tie this all back together, we have y is equal to 1 times x minus pi plus 0. And you could leave it in that form, or I'll write this simply as y equals x minus pi. And it's worth pointing out that one thing you should always focus on, especially for any assignments that you turn in, whether it's a homework or an exam, is that you neatly organize your work. And if you can organize your work as we've done, I certainly can't fault you for doing the same thing that I have. So let's turn to the next page. So we see two functions that we would like to differentiate, and both of them involve in some way, shape, or form at least one application of the chain rule and possibly other differentiation formulas combined with it. I would like you to pause the video, take 5-6 minutes, and differentiate these functions. Okay, so hopefully you've paused the video, you've taken some time to differentiate these functions, and let me give you kind of the quick reminder. If you haven't done so, you certainly should. Remember, you take out of this process what you put into it. So let's go ahead and differentiate. The first function we see is x squared times cosecant of square root x. This is something that we need the product rule to differentiate. So I'm going to go ahead and just for fun write out the product rule, make sure there's no confusion whatsoever what's going on. So we would have the derivative of the first times the second plus the first times the derivative of the second. And note the derivative of this second function, cosecant of square root of x, this is where the chain rule comes into play. So working left to right, the derivative of x squared is 2x by the power rule. Should be familiar and hopefully effortless at this point. Plus x squared times the derivative of cosecant of square root of x. And let me just kind of remind you to the side here that the derivative of cosecant, note it's a co-trig function, so we have negative, and it's negative cosecant cotangent. So by the chain rule, we differentiate the outside function, minus cosecant cotangent. We evaluate at the inside function, square root x, and then we multiply by the derivative of that inside function. And the derivative of square root x is 1 over 2 square root x. And note kind of once again that pattern recognition. You're substituting that inside function in, and then what you end up multiplying by is the derivative of that inside function. And you could do some simplifications here, but to be honest, I would just leave it precisely in this form, and we can very clearly see kind of how you differentiated each term and what rule of differentiation has been used. In the second example, we have sine of cosine of x squared. So this requires us to not only use the chain rule, it requires us to use the chain rule twice. So maybe we'd say twice the fun. Now note, if we just go ahead and approach this exactly as we have done previously, we can think of having an outside function sine and an inside function cosine of x squared. The chain rule tells us simply, you differentiate the outside function cosine, you evaluate that at the inside function cosine x squared, and you multiply by the derivative of that inside function. So we've applied the chain rule once, but every time we apply the chain rule, it leaves kind of this resulting derivative of the inside function. And note, in this case, we really need a second chain rule. So let's continue on. So we have the cosine of the cosine of x squared, which we cut and paste down. And now we differentiate using the chain rule again. The derivative of that outside function, so we think outside function is cosine, inside function x squared. So minus sine, evaluated at the inside function, multiplied by the derivative of the inside function. And once again, I would leave it precisely in this form, and this would represent the derivative of the function sine of cosine of x squared. So note, not only is it reasonable to combine the chain rule with any of our previous rules of differentiation, it's also perfectly reasonable to have multiple chain rules in the same problem. And that finishes our current discussion, but we will investigate even more examples in the upcoming video. So stay tuned and take care.